Your Excellency, embassies and diplomatic court, my fellow colleagues, representations from different stakeholders that we have been engaged during the years, all protocols observed. It is really my privilege to be able to speak on this platform. When I was preparing this thing, I since yesterday have two worries. The first worry is that since yesterday I lost a little bit of my voice. The second worry was that I was afraid that during my presentation that I have to say hello to Douglas, and then I have to light up the plant. But then I was assured by Lynette that this won't happen because we have a diesel generator standing by. So let me start by telling you, everybody knows about this. ESCOM load shedding, stage 1, stage 2, and stage 3. So stage 1 up to 1,000 megawatt, stage 2 up to 2,000, and stage 3 up to 4,000. So this is coming from this picture. So ESCOM can generate at the moment at about 30,000 megawatt. And why you have a variation of demand over the summer and over the winter. So in summer, you constantly need another 1,000 megawatt. And then this rises to 2,000 during the evening peak. That's why we're always experiencing something now like a load 1 and load 2, stage 1 and stage 2 load shedding. And in winter, so we constantly lack 2,000. And then it's going to go up to 4,000, 6,000 to the evening peak. So if you feel that it's bad enough now, so do prepare for the worst to come. What does it mean by 4,000? 4,000 is something that you can expect to coming out of Medupi, which has a built-in capacity of 4,800. And then 4,000 is also something that we have done over the past 10 years. Let me tell you a good story. ESCOM EDSM demand saving over the last 10 years, since 2004, and this is a verified savings that saved us up to 4,000. It means if we would not have this, we would go into immediately stage 3 load shedding. So let's look at the very simple economics, because these are all in the public domain. So the EDSM program has a total investment of 15 billion in the last 10 years. And then it has saved 4,000 megawatt, which is very clean, you don't feel it. And then this is equivalent to about 3.75 million per megawatt. Comparing with Medupi, so the total projected investment is about 170 billion, according to Reuters. And then we know that we have an initial budget of 77 billion. I hope that it's going to stop at 170 billion. And the capacity of 4,800, and then this is equivalent to about 35 million rand per megawatt of power. So comparing with this, we could conclude very simply, 15 billion definitely is greater than 170 billion. So we have already approved this one. So university is a place that we teach mathematics and science and engineering. But university is also a place that we challenge mathematics. So having done this introduction, let me comment on the huge contribution made by the University of Pretoria. So I listed 4 big names in here: the late Professor Yen Lane, Gustav Redloff, and both of them coming from CNES, Center of New Energy Systems, and also Professor Eddie Matthews and L.J. Hrobler. So I think that for a lot of guys sitting here, we know these 4 people. And then they are all coming from the University of Pretoria. And then they actually, when I joined the university, Professor Eddie Matthews is still with the university. I think that the 3 guys already left the university. But then they paved the way for ESCOM to introduce the EDSM program in 2004. So this is what I'm going to talk today. So I'm going to tell you what is EDSM, and then how we can classify them, and then I go further to tell you what is our research in CNAS. And then lastly, probably I'm going to spend half of my time telling, at this time of crisis, do we still have option? And then what are these options? So the whole game is about balance the demand and supply. So in the current circumstances, we either have to increase the power supply, to build new power stations, including renewable ones, and to increase generating capacity from existing power plants, and to decrease ESCOM or the generators' own use, or to reduce the demand, to manage the demand side, to decrease the usage, or to increase its own supply, or we do both. Of course, today I will be only talking about the demand side. So in the United States, energy efficiency and demand side management is classified into 5 big categories: conservation, load management, fuel substitution or fuel switching, load or growth, and self-generation. So let me just very quickly go through each one of them. It's very clear conservation is to use energy less, more efficiently, to save it. Load management is to reduce or shift the peak demand from peak to off-peak. So we'll be talking about this one, given the ESCOM's current situation. So it can consist of peak clipping, valley filling, and load shifting, or flexible load. You shape the load shape. And then load build, of course, is to improve the productivity and the environmental compliances with the increasing sale of kilowatt hours or kilowatts from ESCOM. So it can be something like promoting the electrical infrared technologies as an example to heat or to dry the products such as wood, paper, and textile. And then the benefit, of course, is to increase utilities market share, and then to fill the valleys, to increase the peaks, and to reduce the usage of fossil fuel. Of course, in the current circumstances, this is probably less relevant in South Africa, but remember that load build is one of the interventions that we can do at the demand side. Fuel substitution or fuel switching is the process of switching from one fuel to the other. So it's very clear. Self-generation is to generate heat or power produced for part or complete use of the customer's own needs. So it can be built within the client's or the customer's own processes. In that case, we talk about cogeneration, and it can be self-generation from completely outsized field. So then we are talking about captive power plant. The benefit, of course, is to reduce the demand on the grid and also reduce transmission losses. So this is more or less 5 big categories that the United States and Europe probably also takes the same approach. But for us, we feel it is more beneficial to classify energy efficiency and demand side management in 4 big categories in terms of technology, equipment, operation, and performances. So when you talk about energy efficiency, you talk about technology efficiency, equipment efficiency, operation efficiency, and performance efficiencies. And then you can put the whole puzzle in this way. So you have technology side, you look at conversion, transmission, those rates of conversions. And then at the equipment side, you look at equipment specifications and how to compensate the deviations. And then also you do proper maintenance so that the equipment behaves what is supposed to be under ideal conditions. At the operational level, you look at system coordination, and then also the coordination with respect to time, and also the interface of human with respect to the machine. So you look at the operational levels. And then at the performance level, you look at technical performances in terms of energy or power, all the skills or the so-called soft kilowatt hours, or the theft or losses, which constitute what we call long technical performances. So the advantage of reclassify that into code is that, first of all, it provides a common platform for 4 levels of activities on the same page. So you have activities at the unit level, system level, and the management level, and the policy level. So for instance, if you approach the whole thing, linking all these puzzles together from the outside, you're looking at financial viability. So you look at energy analysis, audit, design or planning, or targeting, or metering, or verification. You can also approach it from the inside. Of course, this is our interpretation. You're looking at energy modeling, energy optimization, and baselining, and then you build some kind of technical viability. So the second advantage is that you can do easy functionality groupings. For instance, that technical impact can be grouped in this way, and then the time impact in terms of power or demand, or the issues related to behavior change. Of course, you can group them in terms of technical performances and non-technical performances. A third advantage, which is very, very relevant for us working in a university environment, is that this framework provides us with a very focused research topic selection for our postgraduate students. So for instance, at the master's level, we look at typically a combination of two function blocks. For instance, from Jaco van Staden, he looked at the model predictive control strategy for load shifting in water pumping with a possibility of reducing the maximum demand. So this is highly related to how to coordinate the system with time, with better energy use or power use with time, and its performances in terms of maximum demand. Udak Ekponion, she looked at, in her master's thesis, she looked at an improved robust model for the generator as the equipment, as well as its maintenance scheduling. And this is related to these two function blocks. This constitutes more or less her master's thesis. In Esrom, Malaj's master's thesis, he looked at possibly a multiple objective optimization model for building energy efficiency decision making, so which is related to how to coordinate different retrofitting components in a building or in a set of buildings, and how the energy performs with respect to that selection. So at the PhD level, for instance, you look at probably more than two functional blocks. You look at probably 4 or more puzzles linking together. In Henrika's PhD thesis that she's going to defend shortly, she looked at the minimum cost solutions of a PV diesel battery hybrid system, which can stand alone, which can be tied to the grid, so which is related to the sizing of the system and also how the system interacts with time. We make better use of, for instance, the time of use tariff, and also the performances in terms of energy and power. In Papi's PhD thesis, he's going to look at more at the optimal energy management of a crusher, of a jaw crusher. And then this is related to that equipment under specific ideal conditions, as well as how it coordinates with other parts of the system, and also coordinate with the time of use tariff in terms of its energy and power performances. And then the other example that I want to run through is Shen Ming's PhD thesis that hopefully he's going to also defend that at the second half of this year. He looked at the optimal sampling plan for a clean development mechanism. This is a lighting project, qualifies for CDM registration, and then with a population dynamics. So it consists of probably also 4 function blocks looking at different ways of measuring the system. So this is just give you a highlight that some advantage that we want to reclassify energy efficiency into POD. So I want to take you through one, maybe going through a little bit of detail, one example, a case study done by Li Jun. He's also sitting here, which is about Exora's co-beneficiation process. So in the background, you could see this last picture, because normally Exora doesn't have a very clear picture of such kind. But you could see that coals are transported to the beneficiation plant, and then a core activity of coal washing happens inside this building. So this is, of course, it's a fake picture, but this is a real picture. So this picture, you could see this building, you could see this building just behind of us. It's about 40 to 50 meters high, about 5 to 6 floors high. So the key process, of course, is a coal beneficiation or coal washing circuitry. So the coal comes into the beneficiation plant. It goes through several key processes into sizing, cleaning, and dewatering. And also the coal is transformed from a coarse size into intermediate size, ultrafine, and fine sizes. And then, of course, if you look at the whole process, the key process is the dense medium cyclone. So if you look into the dense medium cyclone process, so you could see that the run-of-mine coal comes into a mixer or mixing box, and that coal then goes into the dense medium cyclone. And then the rotational movement of the dense medium cyclone generates a centrifugal forces. And then so that the lighter part of the particle accumulates in the middle of that cyclone. So exits from the top part of the cyclone, and then the heavy particles stays at the edge of the cyclone and then exits from the bottom part of the cyclone. And then both goes through a screening process, and then you have rejects, and of course you have the product in terms of what we call fines. And then of course the remains of that thing goes through a median correction process through a corrected median pump, going through this circulation, and it brings back to the distributor and the mixing box, and then go through the process again. So this is of course Exora's core engineering process. And then this technology of wet washing is probably 100 years old, maybe even longer. So there are two issues with this very old design. The first one is energy efficiency. So you could see that the medium pump supplies the dense medium to the separation cyclone are constantly overpumping. So for Exora, I think our estimate is always about 4 times oversized. And then a second issue is the separation efficiency. So there's always a lack of manipulability of the relative density of the medium to improve the product. So to improve energy efficiency, Li Jun suggested a pump storage system, which is a very simple idea. He reckons that if you introduce a secondary median tank in the middle of that building, say second or third floor of that building, you capture that water before it comes to the bottom, and then you introduce a secondary pump which brings this water to the top. And then in that way, you can reduce the height of the water circulation. So of course, then he introduced another option, is that he introduced a third storage tank at the top of that building. So both options gives you very good results from this analysis. For instance, that electricity cost and energy consumption can reduce about more than half if you use a certain type of these storage tanks. So this reduction can be much larger if you have the secondary tank to be higher. Of course, there is a balance that you need to catch enough water, and also a larger storage of T3 is used. And then additional advantage is that you can use this setup to shift the power from the peak to off-peak because you have the storage. So to improve separation efficiency, Li Jun introduced the control system approach. So by doing the modeling of the dynamics of the dense medium cyclone. So if the dense medium cyclone model is taken from another study, which is also carried out in this university by Jonathan Mayer from Exora and Professor Ian Craig in the control group. So we can write nicely what they have described in here into a differential equation. And of course, then you will have manipulable variables U, and then the state variables. The state variable represents the component of ash, sulfur, moisture, and the volatile, the percentages in the fine, in the product and the rejects. Of course, the manipulation variable is the relative density that it can play around, hopefully to control something. So this is I apologize again for Professor Del Rey. You mentioned that I should keep away from mathematics. I promise you, this is one of the 2 slides that I have in mathematics. But the first one I gave you the wrong mathematics. Then I feel obliged to give you some correct mathematics. I want to tell the audience that in the university, at least some groups are doing right mathematics. Okay, so Li Jun then goes further to do the optimization at the operational level. So he introduces 2 controllers, a feed-forward controller and a feedback controller in terms of what we call the model predictive control. So the feed-forward controller uses sample measurement composition percentages of the run-of-mine code feed to the DMC. The closed-loop model controller then uses sampled and delayed state variables, try to do some correction of the control systems. So there are, of course, challenges to implement these 2 controllers. So firstly, the measurement of the composite percentages in the DMC in the overflow and underflow is time-consuming and very expensive, I can tell you. And then I know the Exara is thinking about introducing some equipment to do this more rapid measurement. We're talking about in terms of 10 million euros. So it is, and it is also delayed because the measurement delay can up to many hours, so up to 4 hours. Of course, if you have this 10 million euro, then we can reduce that time delay to about 5 minutes. It is sampled because the data is sampled at that sampling instance, and then there's no measurement any further. So in his proposal, then he used the state of that dense median cycling during the period that there is measurement to predict what is available when there's no measurement. So that's what he called model predictive control. So he also did a lot of extensive simulations to show the effectiveness of these 2 controllers. His idea is to evaluate the impact of measurement delays, for instance, in this graph, on the controller with 5% of modeling uncertainties. So you could see that this is the open loop controller or the feed-forward controller. So you see that without compensation, it drifts away, but you still sit with something like 2.09% of deviations in terms of absolute mean value. And of course, if you introduce the closed-loop controller, MPC, with a large delay of 2 hours, you're sitting with a much better deviation from the set point. So you want to reach a set point of carbon percentage of 75%. Of course, he also shows that the shorter the measurement delay, the better the result is. You see that this error goes to smaller and smaller. And of course, based on this, then he's able to do a life cycle cost analysis for the 2 options. So this is a simple payback period calculation, and then this is done with assumption that you don't do additional underflow or overflow measurement. So without introducing those equipment, you can do manually. The capital investment, the capital cost for the existing system is about 2.25 million. And then, of course, option 1, you are sitting with a much bigger capital cost. Option 2, even bigger. But then the operational cost from the existing ones, you have a considerable reduction in terms of cost. And of course, the maintenance cost will go high, definitely, because you have more dedicated equipment and controllers to maintain. So then you do have accumulated savings. This gives you an easy way to calculate how much you can get your money back. So for option 1, it's looking at about 2.68 years of payback. And for option 2, of 3.3 million years. Of course, this will take time to happen. But then, what is nice about this whole process of engaging Exara is that we quickly identify the so-called quick wins for Exara. So, for instance, that these are the 10 projects that we currently run with Exara. So, the first 5, you look at Exara feels that it will be very much beneficial to introduce energy efficiency specifications for a number of their equipments. I think that this is going to be the first in the country that has a company-wise specifications for, this is probably 80% of their equipment. And then they are also looking at different ways of resizing the pumping system, the crusher system, and the conveyor belts. And then we are helping to design the toolkits or the methodologies to do that. Of course, then, seen as other research areas can be built around the same principle based on the classification of POD. So I want to go through very quickly what are the 5 big categories of activities that we are doing in CNAS. So our first big cluster of activities is on industrial energy systems. It can be mining, the heavy haul trains in terms of speed regulation, fuel saving, and safety driving, and the water pumping systems as well in terms of pumping efficiency and also different combinations of operational control. Secondly, we look at building energy systems. We have a building energy management system developed by ourselves, and we have specifically water heating systems, air conditioning systems investigations, and then we also put a lot of our research effort into building retrofitting and maintenance planning. There's a lot of optimizations going on in there. Traditionally, of course, power systems, you look at generation dispatching, maintenance planning, the electricity market, and the demand response. I know that there's a lot of jargons, but these are still, at least the terminology explains itself what they are. So the measurement and verification, so we offer a service to the municipalities and the ESCOM. So these are all practical projects. We're also running that for the CDAM projects. And further to these services that we offer, we look at the more investigating issues like a socio-economic aspect of the evaluation of energy systems and the scientific mechanisms of measurement and verification. And lastly, renewable and sustainable energy. So we look at different types of systems that I have mentioned, such as PV diesel battery hybrid system, the PV battery grid-tied system, the PV heat pump system, of course, then how these renewable sources can be harvested by the grid in terms of smart grid, for instance. So just to give you some highlights about the achievement in the past 6 or 7 years. So CNAS was awarded to host the National Hub on Energy Efficiency and Demand Side Management since 2008. And then this is already in our second contracting period. And then we are also hosting the Exora Energy Efficiency Chair, started from 2012. And then we publish quite nicely over this past few years. 125 papers, 50 journal papers, things, and then we are building up the momentum. So currently, I think at the current 2 years, we're looking at about 20 or 18 papers per year. So it's quite productive. And then we also edited 1 book. So we have currently a full-time student of 11 masters and a 17 PhD level. And then we have then probably the equal number of part-time students. And then the student graduated in the past 5 years. So we graduated a relatively small number of students, but again, the momentum is there. I think that this year alone, we are looking at graduating something like 4 or 5 PhD students. So we are contracted to offer measurement and verification for ESCOM municipalities, as I mentioned. And then our spin-off company is the first, which is accredited by the Senate against the International Standard Organization 17020. And then in this format, we are running something like 250 projects, 238 plus about 20 from the municipalities. If we look at the hub, so it's probably more, it's going to be a little bit more impressive. So we started in 2008 for the first year of initiation. So this is coming from the audited report organized by DST at the end of 2013. And then it is measured against the number of journal publications, conference publications, registered students, graduates, research degrees, a number of modules, externally funded project, amount of external funding, and of course, very importantly, the proportion of female students and the proportion of the previous disadvantaged individuals with all registered students. So if you look at some of the key numbers, you see that, look at the number here. So we start with a very modest number of students of 27. This is across 3 departments in electrical engineering, mechanical engineering, and chemical engineering, and also a few students from other universities, because this is a national hub. And then this grows nicely until, of course, this is the figure up to the end of 2013, 136. And then the publications also keeps going that one. And then the other last figure is these 2 sets of figures. So we're sitting as 15 female students, and then 15% of female students, and then this percentage. Okay, there's a constant increase of percentages, and then it is stagnated a bit, but it's very difficult to get engineering female students, trust me. So now comes to the second part of my presentation. So I want to come back, all these nice goody things that we've done, do we still have option? So do we still sit with load shedding every Monday to Friday and then possibly Saturday as well? So over the past few months, so everybody is hit by this. And then there's a lot of popular options that was published or somehow comes to our attention. So you have option number 1, which is probably not very popular, but it's ESCOM load shedding. But remember that the load shedding is one of the EEDSM interventions. So I listed here who proposed this. So this is not in absolute terms. This is only for my personal use, because the message first comes to me from these sources. So it's not necessarily that they are first the promoters. So the second one is the pool pump and the geyser control by smart meters proposed by the former ESCOM CEO. And then he reckons that if we would have these smart meters installed, then we would do load shedding in a completely different fashion. And then time zones, of course, this is coming from a number of sources from the South African Chamber of Commerce and Industry, also come from the internal University Pretoria workshop organized by the Faculty of Economics and Management, and then together with the industrial partner AHI, and also business union shift from same South African Chamber of Commerce and Industry, and also switch off streetlights. This is, of course, coming from the public. You have an uproar of people talking about streetlights burning during the day. And then self-generation, and then this is from the Cape Commerce, Chamber of Commerce. And then coal gasification, which I don't know, there must be early promoters, but I think this is one I want to put it under my name, because today, if you read a Star newspaper, so there's a news briefing said that we promote coal gasification technology. Diesel generator and the energy conservation, CFL, LED, solar water heating behavior change. And promoting the use of LPG, also from Cape Commerce of Chamber of Commerce. Hybrid systems with solar and wind solutions, also from the public, or maybe more individualized. So if you look at this list, and then we can go back to look at what ESCOM or what generally the country is doing. So it will be very interesting to see that this list makes up a lot of shortfalls that we see in the existing programs. Let's go back to ESCOM's EEDSM program. So ESCOM EEDSM solutions, I want to put my personal judgment, is a very comprehensive and a very, very sustainable way of looking at the EEDSM side. This is the work plan in 2012. So you see that these solutions is very comprehensive. You look at the technology key in terms of 3 levels of priority, and then it looks at both the energy solutions and demand solutions. And then the solution spreads out from the industry sector, commercial, agriculture, and residential. And then they build these programs into a suite of products or models for the market to choose in terms of ESCO, performance contracting, standard offer. So I listed 10. There are actually more than 10. So, and then for each of these interventions, they have a brief description. They also tell you what is the barriers of these interventions? So of course that you have similar things for 2013 and then previously in 2011. Of course, 2014, nothing much happened because the money was exhausted from the NYPD 3. So if we look back at ESCOM's EEDSM program, so we could easily realize that ESCOM EEDSM focused a lot on conservation and load management, very limited on self-generation. So there is a little bit about cogeneration. And then there is a little bit about power back, but it was failed, I think, at the National Treasury didn't approve this part. So there's definitely not much in fuel substitution. So we don't see much of that. And then there is a new incentive starting from November 2013, 12L income tax incentive, which is a tax incentive look at energy efficiency improvement. You have a rebate or incentive in terms of tax of 45 cents per kilowatt hour saved during the sustainability period of 1 year. Of course, the good news coming out from 25th of February is that this rate is going to be raised to 95 cents per kilowatt hour. So this incentive scheme does allow fuel substitution and self-generation to a limited extent. And then the new announcement does allow cogeneration. So the previous scheme doesn't allow that one. But the current scenario is that 12L tax incentive, in our opinion, is that you still need a lot of buy-in from the stakeholders. So maybe this raise of the 95 cents per kilowatt hour will make a difference. But we can also look at these shortfalls in terms of the POD classification. So let's look at reclassify EEDSM, ESCOM EEDSM projects. So we look at all this, and then this is the classification done by ESCOM EEDSM. So then it is classified into behavior change, operational, and matching or equipment. And then they have also given the possibilities or the potentials of savings for each of these big categories. So you could see that there is almost some kind of a matching with our classification. So you're looking at the behavior change, mostly look at the lost or theft in terms of behavior. And the operation, you look at more about this side, and the matching, you look at the system combination, and then equipment, you look at more at that side. So you could see that what we are lacking, so we're lacking about the programs addressing the skills that can be translated into the soft kilowatt hours. And then we are looking at lack of maintenance, and then we are looking at lack of introduction of new technologies. And the fuel switching, in my opinion, is a new type of technology intervention. So let's just go back to see. So you see that we look at this list of options again. So this is more about the nationwide load shifting proposals. And then you have conservation of switching the lights, and then energy conservation in terms of behavior change, etc. And then there are 5 big categories proposed, either addressing fuel switching or self-generation. For instance, self-generation, and then these 2 are about fuel switching. Maybe there's also a component for self-generation. So I will try to go through this list very briefly, and then I want to evaluate how feasible are these options. And then I will probably, lastly, I will focus a little bit more about coal gasification and the LPG for cooking and everything. So in order for me to do a fair evaluation, so I want to evaluate all these options in terms of affordability and the time frame and the potential of energy savings. In terms of affordability, I look at the capital investment and the operation and the maintenance cost. So in capital investment, I regard it as low if you're talking about less than 1 million per megawatt, which in popular terms, you look at 1 kilowatt, 1,000 rand. That's what I regard cheap. So if it's between 1,000 to 5,000 per kilowatt hour, then we regard it to be median or acceptable. And then I regard it to be very high if it is over 10 million rand per megawatt of saving. Of course, Madupi is very expensive because it sits at 35 million. Then operational costs, I regard it as low if the kilowatt hour cost is below 1 rand. Because we know we are currently paying around 1 rand, depending on how much you consume. So sometimes we pay 1.6 rand per kilowatt hour to the municipalities, but we know that ESCOM's generating cost is about 30 cents per kilowatt hour. So then I regard the maintenance and operational cost to be acceptable or slightly higher if it is between 1 to 5 rand per kilowatt hour. And then anything above 10 rand per kilowatt hour, it is expensive. Okay. And then the time frame I regard to be short term if we can implement immediately up to 3 months. And then if it is between 6 months to 3 years, I say it's medium term. And then if it's longer than 5 years, then we regard it as long term. Of course, then I will comment on the estimated savings for each of this. Let me start with load shedding. So capital cost, no. Operational cost, no, because it's a simple switch. But then the time frame is also very short term. So we are talking about seconds or milliseconds. And the savings, we need 1,000 to 4,000, depending on the demand. Definitely is not affordable, because in no sense it's affordable to ESCOM, because ESCOM is going to lose revenue, and then it's not affordable to anybody. Then smart meters as a smarter way of doing load shedding. So the idea was, the proposal from the former CEO was to introduce smart meters. Because the smart meters comes with it, there's a smart switch inside it, one. And then you can use that one to switch off the swimming pool pump during the day. The idea was that. Of course, then he further elaborated that you can introduce another smart switch to go with the smart meters to switch off the geysers. So you can see that we can easily do a calculation. A smart meter nowadays, a simple one, with that smart switch is about 2,500 rand. Plus installation, you're talking about 3,000 rand. And then you're talking about a typical swimming pool pump of 700 watt. And then, of course, there is a diversification, or what we call utilization factor. So we estimate to be 15% of the swimming pool pump that you can switch off, or they are functioning at that time. So it is very high. So if you do that, it's about 28 million per megawatt hour, per megawatt. And if you want to go further to add another switch, okay, so you can use, the second option is to use that one to control this, the water heaters. Of course, then you are talking also about 15% of utilization, so which is also very high, 10 million per megawatt. And then if you want to do both, then you're talking about 4,500 rand per smart meter and per 2 smart switches. And then you're looking at about 11 million per megawatt. So all these options are very high in terms of capital investment. The time frame, of course, becomes also a problem. So it can be a medium if it is a small size, but if you're talking about large quantities, it can take years to do that. We know the difficulty of doing that one. The savings, of course, it is almost neutral. It only shifts the demand. But the problem is that in order to save 4,000 megawatt, we need 10 million households. I don't know whether we can have 10 million households in the country that has a swimming pool in each of the households and a water heater. So this one, it is a very expensive option, but of course then you are sitting with a very good solution. The operational cost is none. So time zone, this is a very attractive option. So you introduce 4 time zones or 2, depending on different proposals. So we're not quite sure about the capital investment. I guess that it will involve a large amount of logistics. And then it will cause a lot of disorder of the country. But the maintenance, there's no maintenance. So you get used to it, you go. The time frame is median, and then I think that you need to gradually introduce that one. So the best scenario is that you introduce that in a matter of 6 months. And then, of course, then once you introduce, you have to keep that for a long time. But the savings, So this is a well-documented study. So if you want to do time zone shifting, you can look at about 1% of peak shifting, which is about 400 megawatt at the moment. So which is not enough for us to cope with stage 1 load shedding, but it is a very interesting proposal. And then affordability, I think somebody has to comprehend the affordability here. Switch off streetlights, definitely we can tick all the boxes. Nothing. It is affordable. Time frame immediate, you can do that. The savings potential, we're not quite sure, but it can be massive because almost everywhere you go and almost every day you see large blocks of streetlights burning during the day. Of course, during the evenings, you have a lot of streetlights was completely switched off. Fuel switching to natural gas. This is the MTN initiative. So this is a very, very capital-intensive investment. So this employs what we call the IGCC, integrated gas combined turbine. So if you look at these costs, which is about 20 to 25% more expensive than Medupi, but this is a very, very clean technology. So it's been promoted all throughout the world, and ESCOM has got this technology as well. But then MTN decided to do fuel switching, so they want to go on their own. So the savings is very, very promising. So they're looking at about 1/3 of ESCOM bill reduction, and the time frame also acceptable. And then it has a long-term effect on MTN. And then the operational cost is quite acceptable, about 87 cents per kilowatt hour. Diesel generation, this is, everybody is thinking about this because all my neighbors are talking about diesel generation. It is only covered by the regulation of that body corporate that you have to choose a good product. And then, so it can be applied to residential and industrial. And then the capital investment is fine because you're talking about 1 kilowatt hour, 2,000 rand. So then the operational cost is a problem. So our information reveals that you need to spend about 3 to 6 rand per kilowatt hour. But some people say that it can go as high as 15 rand per kilowatt hour, but we regard it to be very high. So we would reckon this is a short-term solution. Definitely is not a long-term solution. Time frame, very short. And then the savings potential, interestingly, Saneti has a study that the industrial installed capacity for diesel generator throughout the country, you are looking at the 3,000 megawatt to 3,500 megawatt, which is equivalent to a full-scale power station. So can we harvest this part of installed capacity? That is the question mark. Solar water heating. So we are looking at very high capital investment, 30 million per megawatt, which is probably on par with Medupi. But the operational cost is very low. And then the time frame, it was supposed to be very short because there was a 1 million solar water heating program. It said that by the end of 2015, we should have 1 million solar water heaters rolled out. But we are sitting at about, I think, less than 300,000 at the moment. And then it can be very long term because of that issue, because there are too many problems. And also the effect of that is long term. So once you install that, you properly maintain that, you can do that for about 20 years. But the problem is the savings. This is the myth, because the 1 million solar water program was designed supposed to save one power plant from ESCOM. But somehow we calculated many times, you need about 8 to 10 million households to do that. Again, we are sitting with whether we have also the solar water heaters that can be installed, rolled out for 10 million households. So the PV panel, again, this is very expensive in our opinion, but it can be reduced with the introduction with more supplies and more costly, effective technologies at 60 million per megawatt. So you see that this is the highest in any regard. The maintenance cost, of course, the operational cost is very low. And then the time frame is very short, given the current circumstances. There's still plenty of supply of solar water panels and the power electronics. But in the long term, so it can become a long-term project, because if everybody goes for this one, it will probably jam the whole traffic. The applicability, of course, is long-term. Once you put in there, you're looking at about 5 years. So the only problem now is this affordable or not? For some people, yes. So we have a system installed about 2 weeks ago, just a short distance away from University of Pretoria. And then this is what the guy called load shedding Moses. So it saves you from the ESCOM's load shedding. So this is the household, which is about 4 to 5 million. And then the monthly expenses on the consumption is about 1,000 kilowatt hour. And then he installed a PV of a peak demand of 3 kilowatt with a battery pack installed in the garage, looks like. And then the capital cost is about 200K. And then you have a saving about 15 kilowatt per day. And then you are looking at about reducing 50% of your bill. So the calculation from this guy, or from this gentleman, is that I have a home loan of about 4 million. Let me take out 5% of it. Then I service my bond. So you can easily do a calculation that you spend additional 500 Rand in addition to your electricity bill. And then it saves you from the ESCOM load shedding, and of course improve your security, and then the kids can still do their homework during load shedding. And then a last thing about this system is that there is a very interesting display online. You can watch it over your cell phone. Of course, it's also displayed in the system, so that how the power flows from these four parts, from the AC to the node, from the PV, and from the battery. So you could see this one definitely is during load shedding, because there's no PV power. It must be during the evening. So there's no AC power. So the power comes completely from the battery. So this is a very interesting one. And of course, a smart engineer will realize that we can probably make it flow in different directions. So one of the options, of course, is to make the power flow back to the grid, which is currently possible. But then, given that you have a feed-in tariff of 2.1 Rand per megawatt per kilowatt hour, it will probably make even better financial sense. And then I want to also comment on that this power flow and the optimization of this power flow is one of the typical things that we do at CNES. So we have at least 2 full-time PhD students and 2 postdocs who are working on similar projects like this one. So let me go to the last one, fuel switching, fuel switching specifically to reduce the heat demand. So I want to make a statement. Let's do fuel switching to reduce the heat demand. So if we do a very quick analysis of the heat demand of South Africa, so this is a study done by a Japanese, and we could see that the heat demand in the residential sector is about 40% of all the electricity demand, and then 70% of heat demand from the industry. And then all these heat demand are currently satisfied by electricity. Let's look at the efficiency, and then why we propose fuel substitution. So we can do an efficiency analysis. So if we go from coal to electricity and to heat, we lose so much. So we're talking about 34%. And then from coal to heat directly, we're looking at about 87%. Of course, this is very dirty because it's a complete combustion process. And then you can look at gas to heat, which is also not very clean, but it can be cleaned. So you're looking at a better efficiency. But from coal to gas to heat, you're looking at about 75%. And then some of the guys in CSIR, for instance, then they can make it in their pilot plant of 78%. So our recommendation is that you reduce heat demand that was satisfied by electricity by burning gas or coal. And then, which makes better sense to burn coal to gas and then to heat, because South Africa is still sitting with a large reserve of coal. So we have close to 70% of coal. Coal is going to stay with us for years and years to come. So we know that we need to go to renewables, but coal is there. And then if we look at the gas, of course, there are technologies to implement it. And then there is a proposal that we import gas from Mozambique. So it is possible. So this one is also a very attractive option. The capital investment for a gas stove is almost nothing, and the operational cost is almost nothing, and then it is very affordable. And then I wanted to give you a very specific example. This is the gas water heating, which applies to the water heaters. So this is the 2014 ETA Award winning product. I hope that Mr. Lawrence Van Niekerk is sitting around here. Yes. Okay. So you see that this is the gas burner, and then it's feed from the normal LP gas. And then to improve the efficiency, then Lawrence also recommend to couple the system with the solar panel so that you preheat the water, so they improve the efficiency. Of course, you're looking at the capital investment. You are talking about 23,000 with the solar panels and about 11,000 without. And then very attractive is the operational cost. You're looking at about 3.5 cents per liter of water in comparison with 12 cents per liter from electricity. So which makes a very, very good sense. Coal gasification, and then the investment is about, I think, acceptable in my opinion, because you're looking at about 1 to 2 million rand per megawatt, which is equivalent to the diesel generator. And then the operational cost can be as low as 10 cents per kilowatt hour, which is about 1/3 of ESCOM's generating cost. And then remember that I said this is coal to gas to heat without going through the cycle of electricity. So time frame is also medium, because I have an example in Bronkhorstspruit. This is the tire factory. So this factory invested about 10 million rand to have that system, which powers the whole plant, the furnace for about 14 megawatt. So you're looking at the daily coal consumption and then the gas production, and it employs about 13 people in addition to their existing staff for the tire factory. The construction only took about 6 months, and then you are looking at about 6 months of payback. So I proposed this guy to look at 12L tax incentive, and then we investigate the feasibilities of 12L, and then the guy didn't even bother. He said, I get my money back in 6 months. Why should I bother? So in addition to that, people might think that you will encourage to use coal, so you're going to use more coal. No, the matter of fact is that if we're going to satisfy these 4,000 megawatt of power by replacing those power by coal to gas, you're looking at about 6% of reduction of the coal consumption. So with this one, I think that my time is also running up. I would like to thank you for your attention, and I'd also like to thank Lynette Smith and your team for the organization, and Shen Ming and Li Jun for helping me to prepare the presentation. Thank you so much.